Hi, good morning, all of you. My name is Srinivasulu, Department of Mechanical Engineering, DBS Institute of Technology in KAVALI. Okay, today I am going to the simple topic stresses and strains. This is the unit number 1, second lecture. Okay, stresses and strains, unit 1. Okay, last class I can explain the define stress, define strains, types of stresses, types of strains, and Hooke's law, modulus of elasticity, Young's modulus of elasticity, and bulk modulus. Okay, these terms are I can explain the last video. Okay, today I am going to stresses and strains relationship. Okay, for one-dimensional truss system. Okay, for one-dimensional truss system, one-dimensional, two-dimensional, and three-dimensional also in your syllabus. Okay, one-dimensional means the forces are acting on the only one direction, that is called a x direction. Okay, two-dimensional means the forces are applied to the x direction and y directions. Okay, in one-dimensional truss system, the relationship between the truss and strain for a unidirectional trusses. Okay, one-dimensional means unidirectional trusses. Okay, is given by Hooke's law. Is given by Hooke's law, which state that when a material is loaded within elastic limit, it state that when a material is loaded within elastic limit, the normal truss developed is proportional to the strain produced. This means that the ratio of the normal truss to the corresponding strain is a constant within the elastic limit. This constant is presented by E and is known as modulus of elasticity or modulus of elasticity. Okay, Hooke's law means the truss is directly proportional to the strain. The truss is directly proportional to the strain. The truss is directly proportional to the strain. In between, the small constant E is the modulus of elasticity or Young's modulus of elasticity. Therefore, the normal truss by corresponding strain that equal to constant. Normal truss by corresponding strain that equal to constant. This means the normal truss is directly proportional to the strain. The normal truss equal to E into corresponding strain. E means constant value, where sigma is the normal truss, E is the strain, E is the Young's modulus of elasticity. Okay, for two-dimensional truss system, for two-dimensional truss system, before knowing the relationship between the truss and strain for two-dimensional truss system, we shall have to define longitudinal strain, lateral strain, and Poisson's ratio. Longitudinal strain and lateral strain and Poisson's ratio. The longitudinal strain means when a body is subjected to a axial tensile load, there is an increase in the length of body. There is an increase in length of body. We can take in the small pipe or small rod. Okay, we can apply to force on a outward direction. So we can apply to force on a outward direction. So okay, when the body is changes its original shape. Okay, the body is changes its original shape because of the length is of the body is increased, the width of the body or diameter of the body is decreases. That is called a longitudinal strain. The strain means change in length by original length. But the same time there is a decrease in other dimensions of the body at right angles to the line of action of the applied load. Okay, right angles to the line of action of the applied load. Okay, thus the body is having axial deformation and also deformation at right angles to the line of action of the applied load. Okay, now the ratio of axial deformation to the original length of the body is known as longitudinal or longitudinal per linear strain. Okay, longitudinal or linear strain. Longitudinal strains also defined the deformation of a body unit length in the direction of the applied load. Okay, let L is the length of the body, T is the tensile force acting on the body, delta L is the increase in the length of the body in direction of P. Then longitudinal strains means delta L by L. Okay, lateral strains. Okay, lateral strains means the strain at a right angle to the direction of applied load is known as lateral strain. Okay, the strain at right angles to the direction of applied load is known as lateral strain. Okay, let rectangular bar of a length L, breadth B, and depth D is subjected to an axial tensile load P as shown in figure. The length of the bar will increase while the breadth and depth will decrease. Okay, let delta L is the increasing length, delta B is the decreasing breadth, delta D is the decreasing depth. Okay, then longitudinal strains is also delta L by L. Okay, the lateral strains also delta B by B or delta D by D as shown in the figure. First figure, we can also the width B and depth D. Okay, na? Next, decreased body D minus delta D, B minus delta B. Okay, next figure, we can apply to force on a outward side, P force. Okay, na? Next, original body length L and change in length body L, L plus delta L. This is the examples of the longitudinal strain and lateral strain. Okay. Next, Poisson's ratio. Poisson's ratio means the lateral strain by longitudinal strain. The lateral strain by longitudinal strain. Lateral strain means the force are applied to the perpendicular direction of the body. Okay, longitudinal means the axis of the we can apply to force on the axis directions. Okay, we can apply to force on the axis of the body. Axis of the body directions we can apply to force, that is called a longitudinal strain. Lateral direction means perpendicular to the axis of the body. We can apply a force on the that body is called a lateral strain. Okay, Poisson's ratio. The ratio of lateral strain to the longitudinal strains is a constant for a given material when the material is trussed within the elastic limit. When the material is stressed within the elastic limit. This ratio is called Poisson's ratio and it is generally denoted by U or 1 by M. Hence, mathematically, Poisson's ratio U equal to lateral strain by longitudinal strain. Okay, Poisson's ratio symbol means mu or 1 by M. Mu or 1 by M, Poisson's ratio symbol. Poisson's ratio definition is the ratio of the lateral strain to the longitudinal strain. So that is called a Poisson's ratio. The Poisson's ratio is very, very important in small answer questions and problems. Okay. Next, lateral strain equal to mu into longitudinal strain. Lateral strain equal to mu into longitudinal strains. As lateral strain is opposite sign to the longitudinal strain. Hence, algebraically, lateral strain is written as lateral strain equal to minus mu into longitudinal strain. This is the longitudinal strain, hence the algebraically lateral strain is written as until the lateral strain is opposite sign. Okay, in this video I can explain the Poisson's ratio. Okay, Poisson's ratio definition and Poisson's ratio formula. Okay, Poisson's ratio symbol. Okay, Poisson's ratio is the important topic in the define. The Poisson's ratio definition is it is defined as the ratio of lateral strain to the longitudinal strain, and Poisson's ratio symbol is mu and 1 by m. Okay, na therefore Poisson's ratio equal to lateral strain by longitudinal strain. Next, relationship between truss and strain. The relationship between truss and strain. Consider a body, okay, ABCD. Consider a body ABCD. We can apply a force on the outward side forces, so sigma 1 and sigma 2, left side and right side, and bottom and top side, sigma 2 and sigma 2. Okay, now we can apply force on a body. Okay, now trusses. Right side trusses sigma 1, left side trusses sigma 1, and upward trusses sigma 2, and downward trusses sigma 2. Next, consider the strain produced by sigma 1. The trusses sigma 1 will produce strain in the direction of x and also in the direction of y. The strain in the direction of x will be longitudinal strain and will be equal to the sigma 1 by E. Sigma 1 means truss, E means Young's modulus of elasticity. Okay, na? In this equation taken from the Hooke's law, means the truss is directly proportional to the strain. Sigma by sigma by strain epsilon equal to E. That is called a Hooke's law. Okay, and that equation we can take in from the strain equal to sigma 1 by E. Whereas the strain is the direction of Y will be lateral strain and will be equal to the minus U into sigma 1 by E. Okay, now consider a strain is produced by sigma 2. Okay, the truss sigma 2 will produce strain in the direction of Y and also in the direction of X. The strain in the direction of y will be longitudinal strain and will be equal to sigma 2 by e, whereas the strain in the direction of x, the lateral strain, in the equal to the minus u into sigma 2 by e. Okay, in these equations are two are normal stresses and longitudinal strains. Okay, lateral strains. Next, let E1 is the total strain in x direction, U2 is the total strain in the y direction. Now, total strain in the direction of x due to trusses sigma 1 and sigma 2, that equal to sigma 1 means sigma 1 by E minus mu into sigma 2 by E. Okay, similarly, total strain in the direction of y due to trusses sigma 1 and sigma 2, that equal to sigma 2 by e minus mu into sigma 1 by a. Therefore, E1 equal to sigma 1 by e minus mu into sigma 2 by e. Next, the E2 equal to sigma 2 by e minus mu into sigma 1 by e. The above two equations gives the trusses and strains relationship for the two-dimensional truss system. In above equation, tensile stresses is taken to be positive, whereas the compressive stresses are negative. Tensile stresses are positive or compressive stresses are negative in this equation. So, okay, per next, three-dimensional systems. So, in three-dimensional systems, we can apply force on a three directions, so x and y and z directions. So, the below figure shows three-dimensional body subjected to the three orthogonal normal trusses sigma 1, sigma 2, sigma 3 acting in the direction of x, y respectively. Okay. Next, the three-dimensional equations are strain equations sigma 1 and sigma 2 and sigma 3 is the three directions, so x and y and z directions. So consider the strains produced by the each truss separately. Okay, sigma 1 and sigma 2. Okay, in this video, we can calculate the sigma 1 and sigma 2 and sigma 3 equations. So that equations are respectively by using of a x and y and z direction. So the trusses sigma 1 will produce strain in the direction of x and also in the direction of y and z, అంటే three directions. The strain in the direction of x will be sigma 1 by e, whereas the strain in the direction of y and z will be minus e into sigma 1 by e. Similarly, the truss sigma 2 will be produced strain sigma 2 by e in the direction of y and strain u into sigma 2 by e in the direction of X and Z. And also trusses sigma 3 will produce sigma 3 by E in the direction of Z. Sigma 3 by E is in the direction of Z direction. Okay. And strain of minus U into sigma 3 by E is the direction of X and Y. Okay. Total strain in the direction of X. Total strain in the direction of X due to trusses sigma 1 and sigma 2 and sigma 3 that equal to sigma 1 by E minus mu into sigma 2 by E minus mu into sigma 3 by E. Similarly, total strain in the direction of Y due to trusses sigma 1, sigma 2 and sigma 3 that equal to sigma 2 by E minus mu into sigma 3 by E minus mu into sigma 1 by E. Next, similarly, the total strain in the direction of Z due to trusses. So sigma 1, sigma 2, sigma 3 that equal to sigma 3 by E minus mu into sigma 1 by E minus mu into sigma 2 by E. These three equations are acting on the three directions X, Y, Z. Okay, now let E1, E2, E3 are total strains in the direction of X, Y, Z respectively. First one, the E1 equal to sigma 1 by E minus mu into sigma 2 by E minus mu into sigma 3 by E. Therefore, next equation sigma 2 equal to sigma 2 by E minus mu into sigma 3 by E minus mu into sigma 1 by E. Next sigma 3 equal to sigma 3 by E minus mu into sigma 1 by E minus mu into sigma 2 by E. These are the three-dimensional equations, so strain equations. So three-dimensional strain equations. So strain E1, E2, E3. Okay, na? Next, trusses are sigma 1, sigma 2, sigma 3. Okay, E is the modulus of elasticity of the material is same. Okay, modulus of elasticity or Young's modulus of elasticity is same E equal to. Next, the above three equations gives the truss and strain relationship for the three orthogonal normal trusses system. Okay, these three equations are truss and strain relationship for the three-dimensional orthogonal normal trusses systems. Okay. Next, this is the truss strain diagram for ductile and other materials. This is the most important topic, truss strain relationship between the ductile materials and other materials. This, as shown in the figure, this component is a UTM, ultrasonic UTM. Okay, UTM mission. This is the universal testing mission. Okay, in this mission, you can test the material property. You can test the material property. Above figure, test specimen. Okay, we can apply to force on a F directions and right directions and left side directions. Okay, na this specimen used in the by using of this component UTM mission, we can apply to the force on the outside and the bottom side. Okay, now next. We can calculate the property of the material in the test specimen middle portion. Okay, we can by using of a UTM mission we can calculate the property of the material. The properties are I can explain last classes. Okay, mechanical properties are 14 properties I can explain. Okay, this is the truss strain curve for ductile materials, most important curve. Okay, this is the truss strain curve for ductile materials, most important topic in this chapter. Okay, truss strain curve. In this figure, as shown in figure, the strain in x directions, truss in y directions. Okay, O is the origin point. O is the origin point. Strain in you can take in the x directions. Truss in you can take in the y directions. Okay, we can also apply force on a origin point. Okay, we can also force on a origin point. The material is changes its shapes. The material is changes its shapes. Ante we can apply to force on a body, changes its original shape. Next, we can apply to force on a body, change its positions. We can apply to force. Force is increased. Next, the body shape is changes. Okay, alternatively. In this figure, OA is the proportionality limit. Okay, B is the upper yield truss. C is the lower yield truss. D is the ultimate truss point. E is the fracture. Okay, that means a failure point. Okay, that means the material is breaking point. Okay, that means the material is breaking point. The truss is increasing, the material, the strain is increasing, the material breaking. Okay, the stress strain curve. Okay, the truss strain curve for a ductile material is plotted using standard test specimens on a universal testing machine. During this testing, various observations are taken and plotted on the graph. We will discuss each of them, these important points on truss strain graph in details. Okay, na? As shown in the figure, first O to A. O to A is the means the proportionality limit. Proportionality limit means the truss is directly proportional to the strain. The truss is directly proportional to the strain. The truss is increased and also strain is increased. Okay, na? The truss is all increased and also strain is increased. Okay, truss and strain also proportionality limit. Okay, okay. Next, that called a O to A portion is called a elastic behavior. O to A portion is called a elastic behavior. Elastic means we can apply to force on a body, it changes original shape. Next, remove the force, it's regain its original shape. That is called a elastic behavior. Okay, best example for the rubber. We can apply to force on a rubber, its original shape is changes. Next, we can remove the force, it's regain its original shape. That is called elastic behavior. O to A is a proportionality limit that material behaves a elastic behavior. That is called a Hooke's law. The truss is directly proportional to the strains. The truss is directly proportional to the strains. That portion is a O to A. That means elastic behavior. Next, upper yield point to lower yield point to next plastic behavior. Next, breaking point to okay na strain hardening necking. Necking means the material is loses its strength. Okay, loses its strength. After the necking point, we can break the material. Okay, this is the truss strain diagram. Next slide, we can explain the one by one proportionality limit to upper yield trusses and lower yield trusses and ultimate trusses and fracture point. Okay, first one, proportionality limit to O to A is the as shown in figure. O to A is the already I can explain. O to A is the proportionality limit to O to A is the proportionality limit. According to the Hooke's law, proportionality limit O to A is the limit where the truss is directly proportional to the strain within the proportionality limit. The truss strain curve is straight line. Okay, the truss strain curve is a straight line. How the truss is increased and also strain is increased because of we can draw the line is straight line. Okay, next. The Young's modulus of elasticity, the ratio of truss and strain for the material is constant within the elastic limit. Okay, within the elastic limit, the Young's modulus of elasticity is also constant. Within the elastic limit, the Young's modulus of elasticity E value is constant. Okay, the proportional limit means OTA portion is a proportionality limit. The truss is directly proportional to the strain. Okay, in this portion is the elastic limit behavior stage and it's follow the Hooke's law. Next, elastic limit to O to B. Elastic limit to O to B. Elastic limit for the material is the limit beyond which the material will not come back its original shape. Will not come back its original shape. Okay, when the external force is removed, when the external force is removed in the truss strain curve from A to B yield point, material exhibits plastic properties. If the external load is increased beyond the elastic limit, the material will not come back its original shape. Next portion is the O to B. Okay, O to B also elastic limit. Next, A to B is also plastic stage and entering into the plastic stage. Okay, in this portion will not come back to the original shape when the external force is removed. Okay, O to A to B is a will not come to the its original shape when the external force is removed. That portion is A to B portion. Next point is the upper yield point. Point B is the upper yield point. Point C is the lower yield point. In this upper yield point, the elastic limit, ductile materials exhibits plastic properties. Upper yield point is the point where the maximum truss is required to initiate plastic deformation inside the material. Strength of a material corresponding to point B is known as yield strength. Point B is known as yield strength. Okay, na? Next, point C is the yield strength. Okay, that point after that point C, the material length is increased with a small with a very small increase in the tensile load. Okay, tensile load truss. In other words, lower yield points, the point where minimum load is required to exhibit plastic behavior in the material. Okay, minimum load is required to exhibit plastic behavior in the material. Next, ultimate tensile strength, point D. A material strength corresponding to the point D on the truss strain diagram indicates ultimate tensile strength of the material. Ultimate tensile strength of a material is the maximum truss a material can withstand before breaking. After this point, nicking starts inside the material. Okay, after the ultimate strength point, after the ultimate strength point, the material is nicking is started inside of the material. Okay, na? In this in this slide, okay, we can explain the proportionality limit, elastic limit, upper yield point, lower yield point, and ultimate strength. Okay, next, this is the rupture or fracture breaking strength point E. Okay, last point in this stress strain curve diagram, rupture, fracture, or breaking strength E. Point E is the point where material fracture or breaks. Stress associated with this point is known as breaking strength of a material. Truss strain diagram comparison for ductile, brittle, and plastic materials. Okay, the most materials available in market can be classified into the three categories. Okay, na? Number of materials are available in the market. Mainly, that components or that materials are classified into three types: ductile materials and brittle materials and plastic materials. Plastic material means we can apply to force on a body. It changes its original position. So after that, remove of a external force, it's not regain its original shape. That bodies are called plastic bodies. Okay, or plastic materials. Ductile materials means we can apply force. The material is mm, the material property is drawn into thin wires or thin sheets. Thin sheets means malleability. Ductile means thin wires. We can apply to force on a body, it drawn into a thin wires. Okay, that is called ductile material. Okay, brittle material means you can break up. Okay, small pieces. It is divided into the, we can apply to force on a body. It is divided into the small pieces or break up. Okay, that materials are called a brittle materials. The best examples are a mirror. Okay, each of these materials exhibits different behaviors. When external force is applied to them, we can understand behavior of these materials by analyzing the structures, their stress strain curves. Okay, as shown in the figure, first figure is brittle materials, second one is the ductile materials, third one is the plastic materials. Brittle materials, ductile materials, and plastic materials. Brittle material means shown in figure, broken pencil. Okay, pencil is a brittle material. We can apply to force on a pencil. It is the broken. Okay, next ductile materials. Ductile material is a wire, ante iron wires. Next plastic material is a plastic components of a spoons, so plastic devices, so plastic buckets. So that is called plastic materials. Okay, next ductile materials. As shown in figure, ultimate truss point and fracture point are not as the same in the truss strain diagram for ductile materials. Ductile materials exhibits elastic as well as in the plastic deformation, copper, aluminum, steel. Okay, now for the examples of the ductile materials, for examples of during the sheet metal bending up to the elastic limit, steel sheets regain their initial position, but after the elastic limit, material starts showing plastic behavior and does not come back its original position. If we continue applying force beyond this limit, material will be break at fracture point. Okay, na? As shown in the figure, the Truss strain curve. Okay, first plastic material, next ductile material, next brittle material. Brittle material, truss is applied. Okay, na? There is no strain. Truss is applied. Okay, there is no strain. Ante strain means change in length by original length. There is no change in length. So okay, there is no change in length. Okay, the brittle material means break up, small pieces break up. Okay, next ductile material. Ductile material means we can run into the small wires. Okay, next plastic material. Plastic material, we can up to the small forces reacting, we can drawn into a the length of changes. Okay, na? That is called a plastic materials. Okay, blue color is a plastic material, red color is a brittle material, middle portion is a ductile material. Next, brittle material. When an external force is applied to a brittle material, it breaks. Okay, when an external force is applied to a brittle material, it breaks with very small elastic deformation and without plastic deformation. Very small elastic deformation and without plastic deformation. For a brittle material is value of elastic limit. For a brittle material is a value of elastic limit, yield strength, ultimate tensile strength, and breaking strength are the same. Okay, in order, in other words, brittle material absorb relatively little energy period to fracture. For examples, brittle material such as pencil, glass will break suddenly with a shaping sound and little deformation. Ceramic, wood, glass, PMMA, graphite, and cast iron are the examples of the brittle materials. Next, plastic materials. Similar to the ductile materials, plastic materials also exhibit elastic properties up to proportional limit. Up to proportional limit. Plastic materials up to proportional limit. But elastic material requires very less stress compared to the ductile material. Elastic material is requires very less stress compared to the ductile materials. To produce deformation, plastic material do not show any work hardening during plastic deformation. For example, when the external force is applied to bend a plastic spoon. Okay, after a certain limit, the plastic spoon will not return its original position. Okay, that is called a plastic zone or plastic materials or plastic material property. Next, small problems. Mm, Problem number one. A rod of 150 centimeters long and diameter of 2 centimeters is subjected to an axial pull of 20 kilonewtons. If the modulus of elasticity of the material of the rod 2 into 10 to the power of 5 Newton per mm square. This is the small problem. Okay, we can find the truss, strain, and elongation of the rod. Elongation means delta L. Okay, first of all, to read the problem. Okay, next to write down the given data. The length of the rod means 150 centimeters. Next, diameter of the rod means 2 centimeters. Okay, next, area. Area means pi by 4 into d power 4. Okay, that is a circular rods. Okay, in this problem is a rod is 150 centimeter long and diameter means 2 centimeters. Okay, but in this problem we can apply to the bar is circular bar. Next, we can calculate the area of the rod. Pi by 4 into d square. Pi by 4 into d square means d means 2 centimeters, that is converted into the mm. Okay, therefore that equal to 100 pi mm square. Okay, now next, axial pull load equal to 20 kilonewtons. So 20 kilonewtons, this is converted into the newtons. So 20 into 10 cube newtons. Okay, therefore next, Young's modulus of elasticity already given in the problem, 2 into 10 power of 5 Newton per mm square. 2 into 10 power of 5 Newton per mm square is the Young's modulus of elasticity. Therefore, to calculate the stress equal to load by area. Truss means load by area. Load means P. We can apply to portion means load. Area means pi by 4 into d square already calculated. Okay, therefore truss equal to P by A. P value is already calculated, 20 into 10 cube or 20,000 divided by A. A also already calculated, pi by 4 into d square, that equal to 100 pi. That equal to 63.662 Newton for mm square. That is a stress value. Stress value means 63.662 Newton per mm square. Newton per mm square means units of the stress. Okay. Next, we can calculate the by using of a equation strain. Okay, na? Strain means E equal to sigma by E. Young's modulus of sigma means stress. Stress by Young's modulus of elasticity equal to strain. Stress is already calculated above. Okay, now 63.662 divided by Young's modulus of elasticity already given in the problem. 2 into 10 power of 5 Newton per mm square. Okay, now Truss means 63.662 Newton per mm square. Newton per mm square also cancelled. Okay, na? Because of we can calculate the strain value 0.000318 is the strain. Ante strain no units. Okay, na? Because stress units are Newton per mm square. Young's modulus of elasticity units are Newton per mm square. Okay, Newton per mm square are cancelled. Next, elongation. Elongation due to the by using of a equation. Elongation means E. Delta L by L. Delta L means strain. Delta L means elongation delta L. Delta L equal to strain into L. Strain into L. Strain already calculated above 0.000318. Okay, now L means the length of the rod already given in the problem. Okay, now this is the calculated. Okay, elongation is calculated 0.000318 into 150. E 150 centimeters. Okay, now 150 centimeters are converted into the mm. Okay, in this problem is small mistake. 150 centimeters is value is substituted in this equation. You also converted into the mm. Okay, next. Next problem number 2. Find the minimum diameter of steel wire which is used to raise a load 4000 newtons if the truss is the rod is not exceed 95 mega newtons per meter square. Okay, na? This is the problem. Mega newtons means 10 power of 6. Okay, 10 power of 6 newton per meter square means 1 newton per mm square. Okay, all values are converted into the mm. Okay, P equal to 4000 Newton. Sigma equal to 95 mega Newton per meter square equal to 95 into 10 power of 6 Newton per meter square, that equal to 95 Newton per mm square. Okay, now sigma value is 95 Newton per mm square. Okay, P means 4000 Newtons. So area means pi by 4 into d square. Pi by 4 into d square. Truss means load by area. Truss means load by area. We can find out the minimum diameter of the steel wire. We can find out the minimum diameter of the steel wire. D is calculated value. Okay, truss means load by area. Load means 4000. Area means pi by 4 into d square. Truss means already calculated, already given in the problem, 95 Newton per mm square. All values are substituted in this equation. 95 equal to 4000 by pi by 4 into d square. We can calculate the d value is 7.32 mm. Okay, this is the small problem. So next, this is the another problem. Find the Young's modulus of a bar rod of diameter 25 mm, of length 250 mm, which is subjected to a tensile load 50 kilonewtons when the extension of the rod is equal to 0.3 mm. Okay, first to write down the given data. Diameter of the rod equal to 25 mm. Area of the rod equal to pi by 4 into d square. Pi by 4 into d square means 25. Okay, next tensile load P equal to 50 kilonewtons. So that equal to 50 into 10 cube newtons. So next extension of rod delta L equal to 0.3 mm. Next length of the rod L equal to 250 mm. Length of the rod 250 mm. Next truss equal to P by A. P means 50,000 by area already calculated in the problem. Okay, we can substitute the all values in the truss equation. Truss equal to P by A, that equal to 101.86 Newton per mm square. Strain E equal to delta L by L. Delta L equal to 0.3, L equal to 250, that equal to 0.0012. Strain value is 0.0012. Next, by using of Young's modulus of elasticity E equal to truss by strain. Okay, na? Truss is already calculated in the problem. Okay, strain is already calculated in the problem. We can also to calculate the E value 84,883.33 Newton per mm square. 1 Newton per mm square equal to 10 power of 6 Newton per meter square. Okay, this is converted into the giganewton per meter square. Giga means 10 power of 9. Next, this is the small problem. Diameter of the rod 3 centimeters. So the gauge length of the bar 20 centimeters. So load at elastic limit to 250 kilonewtons. So extension of the rod 150 kilonewtons. So and 0.21 mm maximum load and total extension of the diameter of the fracture 2.25 centimeters. Determine the Young's modulus. Set a point elastic limit, the percentage elongation and percentage decrease in area. Okay, this is the problem. Okay, now we can find out the area of the rod pi by 4 into d square. We can calculate the d value is substituted in this equation. Okay na. Next to calculate the a value, next truss equal to load by area. Load means 150 into 10 cube divided by area is already calculated in the above equation. To calculate the truss value, strain means increase in length by original length. Increase in length means 0.21 mm. Next, original length means 20 into 10 cube. Okay, that equal to 0.00105. Okay, now that is called a strain. Next, Young's modulus E equal to truss by strain. Young's modulus of elasticity, truss equal to truss by strain. Truss is already calculated in the given problem. Strain is also calculated because of we can calculate the modulus of elasticity. This problem is same for previous problem. Okay, na? Next, the truss at the elastic limit is given by truss equal to load at elastic limit by area. Load is 250 into 10 cube divided by 7.0685 into 10 power of minus 4. That value is calculated to the 353.68 meganewton per meter square. Next, the percentage elongation is obtained. The percentage elongation means total increase in length by original length into 100. Total increase in length equal to 60 mm divided by original length 20 into 10 mm, that equal to 30%. Total elongation of the rod is obtained. Next, the percentage decrease in area obtained as original area minus area of fracture by original area into 100. Pi by 4 into d square minus pi by 4 into d square by pi by 4 into d square, that equal to 43.75% is the percentage decrease in the area obtained by the percentage decrease in the area. Okay. Okay, we can explain the small problems. Okay. And next lecturer I can explain the more problems. Okay, because but you can practice the